Imagine a still pond, its surface perfectly calm and undisturbed, reflecting the sky above like a mirror. Now toss a pebble into it. Watch as it breaks the tranquility. What happens? Ripples, right? They spread out from where the pebble fell, disturbing the calmness, creating waves that travel outward in perfect circles. The universe is similar. Massive events like black holes colliding or stars exploding create ripples in the fabric of space-time, much like the pebble in the pond. We call these ripples gravitational waves. They are disturbances that travel through the very fabric of the cosmos. Albert Einstein, the rock star of physics, predicted these waves back in 1916. His genius foresaw the invisible dance of the universe. His theory of general relativity revolutionized our understanding of gravity. It wasn't just a force pulling objects together, it was a curvature in space-time caused by mass and energy. Imagine a heavy ball placed on a trampoline, bending the fabric beneath it. Einstein imagined these waves traveling at the speed of light, carrying secrets of the cosmos, whispering the tales of cataclysmic events across the universe. For decades they remained elusive, a mathematical whisper in Einstein's theory, a prediction waiting to be confirmed. Could we prove him right? The chase was on. Scientists around the world embarked on a quest to detect these faint ripples, to listen to the universe's hidden symphony. Einstein's general relativity is like a beautiful symphony. It replaced Newton's ideas of gravity with a more elegant and accurate description. Imagine space-time as a giant trampoline. A bowling ball placed on it will create a dip, right? That's how mass warps space-time. Now roll a marble across the trampoline. It won't travel in a straight line, but will curve around the bowling ball. That's gravity. The Earth orbits the Sun in a similar way, following the curves in space-time created by the Sun's mass. General relativity isn't just a theory, it's the foundation of our understanding of the universe on a grand scale. It explains the behavior of stars, galaxies, and even the entire cosmos. Detecting gravitational waves was a monumental challenge for scientists. These waves are incredibly faint, almost imperceptible. Imagine the energy of an entire star converted into a ripple in space-time. Sounds massive, right? Yet these ripples are so subtle. But by the time these waves reach Earth, they are minuscule, like trying to hear a whisper in a hurricane. The challenge was immense. Scientists needed incredibly sensitive instruments, capable of detecting the tiniest of changes. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory, a marvel of modern science. Using lasers and mirrors miles apart, LIGO can detect changes in distance smaller than the width of a proton. This precision is unparalleled. In 2015, LIGO made history with its groundbreaking discovery. It detected gravitational waves from two colliding black holes over 1 billion light-years away. Einstein's predictions were confirmed. This opened a new window to the universe, allowing us to hear events we could never see before. The cosmos was whispering, and we finally had the tools to listen. While LIGO listens to the symphony of the cosmos, a new approach is emerging, using ultra-cold atoms to simulate gravitational waves right here on Earth. It sounds like science fiction, but it's real, pushing the boundaries of physics in exciting ways. Imagine cooling atoms to temperatures just a hair above absolute zero, the coldest temperature possible. At these ultra-low temperatures, atoms behave in strange and wonderful ways, governed by the laws of quantum mechanics. These ultra-cold atoms become like a quantum playground, allowing scientists to create environments mimicking the extreme conditions where gravitational waves are born. It's like recreating a tiny piece of the universe in the lab. Section 5. Bose-Einstein Condensates, a new form of matter. When atoms get ultra-cold, they undergo a bizarre transformation. They lose their individual identities and merge into a single entity, a Bose-Einstein Condensate, or BC. Imagine a stadium full of fans suddenly acting as one giant organism. That's a Beck. In a Beck, atoms behave like waves, overlapping and interfering with each other. This quantum weirdness creates a perfect medium for simulating gravitational waves. Think of it like using ripples in water to study waves in the ocean. By manipulating these ultra-cold atoms, scientists can create ripples that mimic gravitational waves. This allows them to study these elusive waves in a controlled environment, something impossible with astronomical observations alone. Section 6. Recreating the cosmic dance in the lab. Imagine two black holes spiraling towards each other, a cosmic dance of incredible energy. This event generates gravitational waves that ripple through space-time. Now imagine recreating this dance not with massive celestial objects but with ultra-cold atoms. That's what scientists are doing. They use lasers to trap and cool atoms, creating a BC. Then they manipulate the BC to create ripples that mimic the gravitational waves produced by those spiraling black holes. By studying these laboratory-created ripples, scientists can test Einstein's theories with unprecedented precision. It's like having a miniature universe where they can control the parameters and observe the effects of gravity up close. Section 7. The power of collaboration. Physics embraces the cold. The groundbreaking research in simulating gravitational waves with cold atoms is a testament to the power of collaboration. Physicists specializing in general relativity are joining forces with those at the forefront of atomic and condensed matter physics. This fusion of expertise is crucial. It's like combining the knowledge of a master architect with that of a skilled builder. The result? A stunning edifice of scientific discovery. This cross-disciplinary approach is becoming increasingly important in modern science. As we delve deeper into the mysteries of the universe, collaboration between different fields will be key to unlocking new knowledge. Section 8. A universe of discoveries await. The ability to simulate gravitational waves in the lab opens up a universe of possibilities. Scientists can now study these waves in ways never before imagined, potentially leading to groundbreaking discoveries about the universe and its fundamental laws. Imagine testing Einstein's theories with unprecedented accuracy, probing the mysteries of black holes, and even exploring the nature of dark matter and dark energy. These are just a few of the exciting avenues that this research could illuminate. The future of gravitational wave research is bright, and the use of ultra-cold atoms is adding a new and powerful tool to our arsenal of scientific exploration. Section 9. Beyond the horizon. The quest to understand the universe is a journey without end. It is a voyage that has captivated humanity for centuries, driving us to look beyond our world and into the vast expanse of space. With every new discovery, new questions arise, beckoning us deeper into the cosmos. Each answer we find leads to more mysteries, more puzzles to solve, and more frontiers to explore. The simulation of gravitational waves with cold atoms is not the end of this journey, but a new beginning. This groundbreaking research opens up new avenues for understanding the fundamental forces that shape our universe. As we continue to explore the universe, both from the vastness of space and the precision of the laboratory, we can expect even more surprising and awe-inspiring discoveries. The collaboration between astronomers, physicists, and engineers is crucial in pushing the boundaries of what we know. The cosmos is full of wonders, and humanity's thirst for knowledge will continue to drive us towards them. From the smallest particles to the largest galaxies, every discovery brings us closer to understanding the grand tapestry of the universe. The future of science is filled with promise, and the study of gravitational waves, whether through cosmic observation or laboratory simulation, is certain to play a leading role in shaping our understanding of the universe for generations to come. The journey is long, but the rewards are beyond measure, promising a future where the mysteries of the cosmos are unveiled one discovery at a time.